a bit different. We'll talk about TTA a little bit, and then we'll talk about exciplexes, because exciplexes are starting to get interesting again, and we want to try and see if the theory of ICT molecules works for exciplexes as well. All right. So first of all, let's think about TTA. All right. Just to point out a few things about triplet-triplet annihilation. It's all been published, so you can go and read about it, but I just want to point out a few highlights and then show you where TTA comes into some of the observations you get in some of the photophysics. The first thing I want to point out, if I slip into calling it triplet fusion is the part of the triplet-triplet annihilation process which regenerates the singlet. Right? So I'm going to, in a way, you differentiate between the bad part of triplet-triplet annihilation, where you lose your excitations, or it remains the triplet, compared to the process you do want, where the two triplets form a singlet. Right? So its proper name is triplet fusion, but then that's a sub part of TTA. All right. So I think everybody knows this. We'll start with this to start with, yeah? So you know that when you get two triplet states, whether they collide in solution or one hops and finds another one in solid state, the two triplets can form some kind of encounter complex. So they merge together. They can either sit on two molecules and merge, which is probably the first two states, which is an encounter complex which has overall singlet character. Right? And there's 1 in 9 ways to combine the spins to get, that's the spins and the sub-levels of the spins. There are 1 in 3 ways that you end up with an encounter complex which is a triplet state. And there are 5/9 which are states which have quintuplet character. Quintuplet character means it's got 2 spins pointing in the same direction, which means that the excitation now sits on 1 molecule. So it's effectively a doubly excited molecule. And if you do the theory of a molecule and put 2 excited states on it, you'll find it costs you an awful lot of energy to do that. So most people, even if you go back in the literature a long way, so probably the best photophysicist ever is this guy Birks, who was at Manchester. If you get a chance to get the old photophysics books that he wrote, even we've only got photocopies of them, right? All the answers are in there. You can actually delve into his books and you might well find the answer to stuff already. The guy is amazing. Right? He had this idea that triplet-triplet annihilation involved this quintuplet states, and it depends what the quintuplet state did and how the quintuplet state might end up forming a singlet or a triplet. So he thought that basically when the 2 triplets combined, right, you'd end up with 3 triplet states and 2 singlet states as a result of the way in which these encounter complexes decayed. So he thought you'd actually get 40% singlet production in total from triplet-triplet annihilation. The group in France by Santil again worried about this quintuplet state. And effectively they kind of said, well, most of the quintuplets would just fall apart. They're too energetic. And they'd fall apart and form 2 separate triplets again. And so they reckon you get about 20-22% singlet formation. Right. So if you just go on this plot, or this is schematic, then you'd say 1 in 9 of the encounter complexes would give you a singlet. So for 18 triplets, you'd get 1 singlet, about 5%. So you could either believe that TTA would give you 5% triplet production, 20% triplet production, 40% triplet production. What it really depends on is what this quintuplet state actually is it stable, or is it just the triplets come together and fly apart again? Okay? That's where some of the confusion about TTA comes from. You can tell that you've got TTA going on by doing the intensity dependence of your delayed fluorescence. So we say that two triplets form the counter complex. Some of those give you a singlet state, and the singlet state emit. It doesn't matter at the moment about what percentage of singlets you get. You now know that you make two excited states, and you end up with one emitting state. So you've got to put two photons in to get one photon out. So if you look at the intensity dependence of a TTA process, then at low intensity, so low triplet population, you get a quadratic dependence on the power. Right? Two photons in, one photon out. When you get to a very high triplet density, it turns over to linear. If you do the maths, you basically say when the triplet population is high enough, then the amount that comes back as TTA is small compared to the total population. It effectively looks linear. It also means that the actual motion and the movement of the triplets is different, and I'll show you that. Okay? So the main thing you look for TTA is a slope which is quadratic and then linear. Okay? And there is another catch. It's not 2 and 1 slope. It's this quadratic part is the square of the power dependence of the linear emission. Because the linear emission might be suffering from quenching, and you might not have pure linear dependence on power for the fluorescence. And so the emission that comes from the singlet states that you generate from TTA must follow what the linear emission does. So it's actually it's the square of the power dependence of the linear. So you can have something which is like 1.6 and 0.8, and it's still TTA. Yeah? But you want to look for this thing that's got this well-defined knee and turnover. All right, so for TADF, it's linear. For prompt emission, it's linear. For TTA, it's very different. So you can really tell the difference between what processes you've got. That's helpful because when you get a mixture, so I'm going to talk about some systems where we get TADF and TTA at the same time, you can use this to actually tell that you've got this double process going on. Okay. I put this in because Carsten is here. Carsten spent his life trying to measure these damn diagrams and understand what goes on with triplet migration. So the idea with triplet-triplet annihilation, you've got to have two triplets find each other. And we're not doing this in solution, we're doing it in solid state. So the triplets have got to hop incoherently to find each other. Okay? So when you hop, you move downhill in energy. So every time a triplet hops, it loses a little bit of energy. And so in schematic terms, if this is the Gaussian density of states, the GDOS, as theorists love to call it, right? When you first excite the system, so you hit it with your laser pulse, you make this population of triplets, and they have all different energies. Right? Some have got very high energy, some have got very low energy. So that the triplets with high energy, it's very easy for them to hop, because it's going to be easy for them to find a state which is at lower energy to move to. Okay? So the hot triplets start to hop quite quickly, right? And you start to move everything down to lower and lower energy states. As you do that, it then gets harder to find another lower energy state to hop to. So as you move, as the average energy of the triplet states decreases, the hopping time decelerates, because it's getting harder and harder for the triplet to find another site to hop to. So as you cool down by this hopping, the actual hopping rate of the triplet slows down. So the hopping rate of the triplet becomes time dependent. So it's dispersive transport. It's only when you get to thermal energy, KT, right, then there's always KT energy there. So the hopping rate of the triplets is always the same. It's constant because it's got that KT energy. So that's non-dispersive transport. So what you tend to see is if you look at the hopping rate of the triplets, it decelerates, and then it plateaus when it reaches KT. So you go from dispersive transport to non-dispersive transport. So when you then think about, well, these two triplets have got to find each other, then the rate of triplet-triplet annihilation is also time dependent, because it takes longer and longer, the longer you wait for the triplets to find each other. So this dispersive and non-dispersive transport of the triplets directly affects the rate at which TTA occurs. So when you look at things like the time dependence of the TTA process, you have this kind of hidden time-dependent mobility of the triplets underneath, which complicates things a lot. Right? So when you see photophysics involving TTA, there's a lot more in those plots than just simply saying, oh, the triplets are just moving. Okay? And then, I didn't put the rest of it in, but go and read Carsten's papers, because some of them are very pretty about the matching experiment to theory. All right? So, we take the point, we've got the triplets and they do find each other. Okay? It's time dependent, but they find each other. So, how many singlets can we realistically think that we'll produce? So, big assumption. We'll say that all these quintuplet states, we say they don't count. Basically, you can't form them. It costs too much energy. If you do calculations and try to put 2 excitations on most of these molecules, the energy cost is so vast, the molecule will fall to bits. You'll break a carbon-carbon bond before you put 2 excitations on one of the molecules. So effectively, they come together, and if they think they're in they try to go into quintuplet form, they just bounce back off each other. But that means the triplets go back into the pool to go find another triplet. So what we want to do is, what we think about is that 1 in 9 of the encounter complexes immediately forms a singlet state and emits. That leaves the rest of the triplets to carry on annihilating. So the 1 in 3, which form a triplet encounter complex, and you end up with an excited triplet state and a ground state, just simply lose you 1 excitation. The triplet that's in the excited triplet state will lose its energy, but it's still a triplet and then can go off to find another triplet to annihilate with. So what you have to do is you've got to add up every encounter until you use up every single triplet. And if you do that, and you say that you ignore these quintuplets, then you'll get 20% singlet production in total, if you use up every single triplet. And they go around the loop until they're all gone. Okay? So that means that in a device, if you've got a fluorescent blue emitter, which is very efficient at doing TTA, then you will get 25% singlet production, and then of the 75% of triplets, 20% could annihilate to give you another singlet. So in total, you'll get 37.5% singlet production. So for a typical blue emitter that you use in displays, then you're getting somewhere in the region of this kind of performance. So TTA doesn't increase the emission by 5%, it increases it by something like 40%. And you get a total of 37.5% singlet production. So that's why at the moment people use blue emitters with strong TTA, because it's better than a single fluorescent emitter, but it's not as good as a phosphorescent emitter. Okay? If you draw it on an energy diagram, basically the way people think about this is that the two triplets in the encounter complex come together. Quantum mechanically, the spins can combine and it becomes a singlet state automatically. That's fine, that's the straight singlet production. The ones that have triplet character, when the encounter complex decays, it's a bit like energy transfer. So one of the triplets transfers its energy to the other. It goes up to a higher excited triplet state, and the other one goes back to the ground state. So that's why the two triplets come together, you lose one, and you end up with one excited triplet. So that's this process. That relies on the fact that the two triplets have enough energy to form one triplet in the excited state. What happens when the two triplets don't have enough energy to form a triplet in the excited state? So the two triplets come together, you can't get energy transfer to the excited state and go back to the ground state. So they sit there going, what do we do, guys? And they fall apart. And they go back to being two triplets and go around the loop again. So that means that the only way that the triplets can decay when they form an encounter complex is by the singlet excited state, as long as the energy of the two triplets is more than the singlet energy. So if you can construct a molecule where twice the triplet energy is less than the triplet excited state, but more than the singlet excited state, TTA should give you 50% singlet production. So if two triplets come together, the only way they can decay is via a singlet state. So 2 becomes 1, you get 50% triplet yield. If that can happen, you'll get 67%, isn't it? 62.5% efficiency in your device from TTA. Now the problem is, two problems with that. No one's ever seen a fluorescent emitter that's got an internal quantum efficiency of 60%. If we ask Christoph nicely, he might tell us, I don't know, external quantum efficiency of 9 or 10% for the best blue TTAs? Yeah. Yeah. So that would equate to perhaps 40%, yeah? But never 60%. You can, in principle, get a molecule that fulfills those criteria, where twice the triplet is less than the triplet excited state, but more than the singlet state. Actually, what you find is you tend to end up, the two triplets are resonant with the singlet excited state. So rubrine or anthracenes, right, twice the triplet energy is definitely less than the excited triplet state, but it's resonant with the singlet state, which means it's just as likely for the two triplets to form and go to the singlet as it is for the singlet to split to two triplets. So you get triplet fusion and triplet fission. So the problem is, in the molecules where you might be able to get this really strong, efficient TTA producing singlets, you're in competition with singlet fusion. In fact, these molecules, like anthracene, are the ones that people use in solar cells to get singlet fission to get two triplets. So even if you've got a molecule where you think you might get really enhanced TTA, you probably lose because all those singlets are splitting off the triplets again. Okay? But in reality, and what the best molecules, TTA molecules, do in devices is probably somewhere approaching that 40% singlet production. Okay, so that's where it comes from, and that's how you can get much more singlets than the 5% that the 1 in 9 would normally give you. Okay? So that's TTA. So let's have a look at devices. Oh, I forgot I put this in. This was work with CDT, how old this work was, using a polymer to try and work out how much TTA was actually enhancing the performance of the polymer in a polymer OLED. What Simon King did, so he was one of our PhD students and went to work for CDT, is he made a polymer device with a polymer emitter and he added a triplet quencher. So if you look at the performance of the device without the quencher and with the quencher, you can see that if you quench the triplet states of that fluorescent polymer, the device performance was definitely much worse. Right? But you tell me that triplets don't form any light in a device. There you are. This is living proof that the TTA process is giving you quite a lot of light in that device. Okay? There's no heavy metal, there's no nothing, it's just a normal polymer, and that's the triplet contribution from TTA in the device performance. If you look at, this is, it takes a long time since I looked at this, right, so if you look at the induced absorption of the device, you can look at the triplet population in the OLED. And if you look at the triplet population in the OLED without the triplet scavenger, you can see strong triplet population and the triplet population growing with applied bias. But you put the scavenger in and all the triplets have gone. Interestingly, if you looked at that same device without the scavenger that had been running for quite a while, the triplets were gone as well. So we think some of the really rapid decay of an OLED is you're getting rid of the triplet-triplet annihilation contribution. It's easier because the triplets migrate so much, they'll find any quenching site. So as soon as you start making quenching sites, the idea was you might well just be quenching the triplets. So that was one idea. The real key to this was to prove that it was TTA was when you look at the afterglow of the device. So you do the experiment. Pete talked about it yesterday where you have the device running and you switch it off quickly and you look at the light given off. Okay? So in blue, this is the triplet population that you measure by induced absorption in the device after you've switched it off. Okay? The light blue is the square of that triplet population. The red is the delayed emission coming from that device after you've turned it off. And you can see that the slope of the square of the triplet population is identical to the light decay. So the delayed light coming off has the same form as the square of the triplet population. So it's TTA. Even clever, Simon was quite a clever guy. Up here, he turned the voltage, he put it into reverse bias. So after a while, he put reverse bias on the device, so he stopped the charges, he quenched the singlets with the reverse field, 10 volts. So it didn't generate, because it's reverse bias, it didn't generate any new charge or anything. You just put a really big voltage across the device and you quench the singlets by the electric field. Right? So you quench the singlets, but the triplets, and then you turn the voltage back off and it comes back on again quite happily, finding itself. Right? So it's definitely, the light's coming from the triplets. The triplets are forming singlets. You can quench those singlets that are formed by electric field, but once you switch electric field back off, it just follows exactly the same line. So so all that delayed emission coming out of the device after you've turned the field off, is from TTA in this polymer. Right? And you can see the effect that you get on the improved performance.
Could you explain the dimension of the value of EL intensity? Is the derivative of intensity?
No, that's just the EL intensity. This is...
So what's the dimension of this value?
I know, sorry. This is the EL. This is the induced absorption. So there's effectively two plots on one graph. Don't worry about it. It's just to show you how the decay curves fit each other. Okay? All right. Yep.
I think I've probably missed that. What the concentration?
Right. So this is, the blue is the triplet population in that device after you've turned the field off.
What the concentration of
Oh, no, it's a polymer. It's a pure polymer. Just a simple pure polymer. Yeah, that's all it is. All right? Yep. All right, that's photo-induced absorption. So you look at the absorption from the T1 to the Tn state, right? And you can see that because it sits in a place where the emission doesn't overlap, and you just use that as a measure of the triplet population. And all we're interested in is just the decay. We're not interested in the absolute number because you fit the decay trends, and you can see if it goes as linear or square with that population. Yeah. Okay.
So the efficiency of this process would depend on how far your triplets are.
Yeah, because it also depends on the density. The density is higher, you get more TTA because they're closer together. Yeah. Right. So you can see what TTA does for your device. The triplets aren't all bad, but they're not as good as phosphorescence, and that's why we use phosphorescence. Okay? But we want to bear in mind that process, TTA, will give you delayed fluorescence. And you'll get a delayed fluorescence signal if there's TTA. So when we go and look at TADF, right, which is the delayed fluorescence from triplets, we want to look carefully as well to see if there's a TTA component as well. Okay? So in most of the ICT complexes that we've measured, we only ever see really pure, almost perfectly linear power dependence. Right? We see pure TADF. We never see a contribution from TTA in those ICT molecules. But let's look at exciplexes. So an exciplex is an excited state complex between a donor and acceptor that just don't happen to be linked together chemically. So that's the old-fashioned way of making a charge transfer state. And of course it's a charge transfer state because you excite the molecule and you get charge transfer to the other molecule. Okay? So we have another way of making a CT state. The idea being again that the CT state is going to have very small exchange energy and we'll get TADF. So one of the first exciplexes that came out of Jahira Adashi's lab was this one, which was quite strange, MPD and TPBI. So it's a whole transport and electron transport material mixed together. Right? Very simple. One-to-one co-evaporated. And if you look at the LUMO of both those molecules and the HOMO, you can see that it should form quite a nice charge transfer state. And there's a nice gap between the LUMOs and the HOMOs to give you a driving force for electron transfer. You look at the spectra, right? So you're now used to the fact that when we have the CT state, the CT emission is redshifted miles away from the emission of the donor and acceptor. You wouldn't call that miles away from the donor and acceptor. Yeah? So it starts to look debatable. Is that really a CT state or not? You look at the time decay of the emission. The solid colours are just the MPD, if I remember rightly, and the duller colours that you can hardly see are for the eczema, the mixed state. And certainly the eczema emission, even though it doesn't look very different, has a slightly longer lifetime. Not much, it's only a factor of about a nanosecond longer. So there's some interaction between these two that forms a slightly longer lived state. So we termed it a very weakly interacting pair. Okay? The problem was that the PLQY of MPD is 35% and the exciplex was less. So the exiplex was worse than just having the MPD. So, but anyway, we persevered and we looked at the photophysics. What we found is when we started to look at the time-resolved emission, what we could see is that, yes, most of the emission was coming out of the NPD. And there was a little bit of emission coming from what we loosely could call an exiplex state. Okay? But then we looked at the phosphorescence and we found that the triplet of the MPD, is it MPD? Yeah, it's a triplet of the MPD is much lower than even the exiplex state. Is that the right way around? It isn't. The MPD is the quencher in this one. Yeah, right? So the problem here is that, yes, you could make the exiplex state, but the triplets were always going to quench it. So in fact, what we were probably doing in this exiplex was actually getting a new route to making triplet states more efficiently than the MPD was making triplet states. So we were getting a higher triplet population in this system. Then we looked at the decay of the intensity, and you can see that we get a prompt emission. Then we get an emission which is going of the power law of about 2 and then turning over to a power law of about 1. And you look at the intensity of that delayed emission. Oh, and the slope is 2 turning over to slope 1. Aha! So in this system we get an almost pure TTA. No TADF, it's TTA. Right? So by looking at the decay of the emission and doing the intensity dependence of the emission, you can immediately say this isn't TADF, this is TTA. So what's actually happening in this system is, yes, you're getting TTA. If you make a device with that exiplex structure, right, it's terrible, but the EQE is probably twice as much as the PLQY would suggest. So what it's saying is that the TTA is contributing quite a lot to the amount of light in that device. It's still a terrible device, it's only a few percent EQE, but the TTA is giving you an enhancement. And so Gyro Dashi thought this was TADF, it wasn't, it's TTA in this experiment. So this is why you've got to measure all these different photophysical properties to find out exactly where enhancements are in devices. Right? And so basically what we think is happening is you excite the NPD and you get some prompt emission. You form an exiplex which gives you more triplets in the NPD. You then get triplet fusion which gives you some NPD emission back and some more triplets and more exiplex. You just keep going round and round this loop. So you can see a little bit of exiplex emission, but most of the emission is coming from TTA, which is the NPD emission. So you can understand the photophysics of that system. So it's not very good, it's not very useful, but you can start to understand what's happening. And if you add up all the various contributions that would give you singlets, you can come out with a total EQE, which is about what you measured. Okay. So then we went to look at a better exiplex. And it's not the best exiplex. All right? Somebody on the front row has got the best exiplex at the moment. He's smiling because his exiplex is very good. Yours. So this is MT data and PBD. Right? And for some reason, MT data always forms really good exciplexes. In some of our presentations last night on the Exilight project, all the systems had MT data in, they formed CT states and exciplexes, and all the others didn't. Right? So simply to say that if you've got an overlapping homo-lumo level of donor acceptor will form an exciplex, nah, there's a lot more to it. And we don't understand it at all. Okay? But anyway, this pair does form a strongly interacting exciplex. Right? So Jahira Dashi, and he's now Professor Gushi, isn't he? Uhei? Isn't he now? He's got a permanent position now in, I think. Yeah, he definitely is in Foucault. So they measured this system and they thought that the singlet-triplet gap was 50 millielectron volts, and it was a fantastic TADF molecule. Right? Now certainly when you look at the energy levels, then the CT states are a little bit below the local triplets. But actually, you look at this, you see that the local triplets and the CT states are quite close in energy. Right? And where have we seen that before this morning? Okay. You look at the spectra, and you can see now that if you look at the emission of the empty data and the TPBI, and not TPBI, this is the empty data and a film of empty data, and the Xiplex. Empty data forms dimers. It dimerizes. Right? So as well as seeing the donor-acceptor emission, you get emission which is coming from a dimer state of the empty data, and when you put the two together, the PBD and the empty data, you get a very strong, very redshifted CT band. So there are two excited states forming in there you have to be careful of. And it's a real ground state interaction because you can actually see a new absorption band at high concentration of empty data. So it's not an excimer, it's a real dimer, a ground state interaction. Okay. And then if you look at the time resolved emission from just the empty data, you can see that that dimer state has a much longer lifetime than the prompt emission. So this state is the dimer, it's much longer lifetime than the state of the empty data. So
how do you achieve that your materials form dimers? And only dimers?
well, this is the pure empty data on its own.
Okay, but when you have empty data PBD, right?
So most of it is Xiplex because the emission is really shifted.
Okay, if before you do the measurement, you do the device, right? So in that, or in this material, you have dimers only. How this happen?
No, in empty data you have dimers. In this system, are we going to have dimers and Xiplexes coexisting? That's the question. Okay? So I'm just saying, if you have empty data on its own, it forms a dimer state readily. And now you mix in the PBD, all right, what's going to happen? So obviously, if you just look at the emission spectrum, you look like you get strong CT emission, all right? You can't see this weak dimer emission, but it might be there. And let me show you that it is there, all right?
Okay, I'm just curious about the structure, right? Structurally, if I put two things together, right? If they're not miscible, then if they separate, I don't have these dimers.
No, that's a dimer of the empty data on its own.
Yeah, I mean,
but without PBD.
Empty data PBD.
Yeah.
Right? So you must have empty data PBD and empty data PBD, empty data PBD, but not trimers, not tetramers, not monomers, right? All of that is possible in stuff.
Yes. But it's the Xiplex is stable just across two of them, and it doesn't matter about the others.
But suppose I wanted, so how do I force them together?
You can't. No, that's luck. You make the film, and that's what you get. So, right. Yeah. Okay. So, we then looked at the decay dynamics of the empty data PBD. Right, so you're used to looking at these decay dynamics of the ICT systems. So now if you look at this, you see this what we would normally call this initial prompt decay is actually tri-exponential. Right? And the longest lifetime is 300 nanoseconds. Right? This second step, which you think, oh, that's the DF, Right? It's not the DF. Right? So this bump here, right, isn't DF because it's present in the pure MT data film as well. Same lifetime. Right? It's there. That's the MT data dimer emission. Right? So this is just dimer emission. It's not the TADF. Right? But the good thing is that this is one of the best TADF traces we've ever seen. Right? It's the fastest TADF, and it's very, very strong. So the gap for TADF, and it's thermally activated, this part, right, is tiny. So the TADF there is better than most of these ICT molecules. It's a bit complicated because you've got this dimer state in there as well, and you're still getting phosphorescence, something down here. This is a power law. Right? This light is decaying with a power law. And if you look carefully, a lot of the decays, you'll see this power law decay at long times always. Right? We don't know what gives rise to that power law. All we do know is it gives you the same emission spectrum as the CT state. So, being honest, half of this decay curve, we don't know what it means, apart from the fact that it's still giving you CT emission. Right? But this stuff is fantastic because even at 16 Kelvin, we get the same really long-lived emission. Right? It's still TADF at 16 Kelvin. So the gap must be... Right? However, remember, this gap might not be a thermal barrier. If this is the same mechanism as in the ICT molecules, we just need vibrations to mix two states. So this might not be a true thermal gap. It might just be that you've got a very low energy vibrational mode which is coupling your states to allow the TADF. Right? Because in this situation, the charge transfer now is even further apart than on an ICT molecule. So the CT states are going to be exactly the same energy, and there's going to be no spin-orbit coupling whatsoever. So we have to come up with a mechanism in the exciplex to give you TADF as well, to give you the spin flip. Okay? Yeah?
Your experiment is 16K.
Yep.
What's the local temperature?
Well, this is a question about what is temperature and where does the excess energy go in the molecule and stuff like that.
Oh, yeah.
Yeah?
Because you could be a significant...
Exactly. Maybe. Well, you've probably got that excess energy exciting all the vibronic modes of the system. Yeah? Which will then couple. But then, why in some materials you get to 77 Kelvin and it's gone? So there's the counter argument as well. So I don't know what local temperature means anymore in these molecules. Yeah?
So you said your couple is further away than in donor receptor molecules. I don't know whether this is true because typically these diamonds are pi-stacked. So positive and negative charge are typically only 3.5 angstroms.
Yeah, that's right. The typical separation between two molecules is about 3.5 angstroms, and then where are the charges? Yeah. I'm not sure.
Whereas in these long donor receptors...
Yeah, but no, I mean, well, in the ICT molecule, it's from the donor acceptor. It's across the carbon-nitrogen bond. So it's much closer in them.
But I mean, if they are really pi-stacked and they...
This might be the reason why MT data is very good at forming exciplexes against TADF and others don't, because you've got to really get pi stacking. Yeah? So we don't know much about exciplexes at all. Yeah? The good thing is that you measure the delayed fluorescence. Yep, brilliant. You measure the delayed fluorescence at all different temperatures. It's always linear. Right? It's always TADF, not TTA. And when we did it carefully, we analysed the temperature dependence of the intensity. Right? You can see at high temperature, you reach this maximum again, which is a bit like in 2K. You reach a maximum in the DF here, and then it decays away as you cool it down. But what we actually found, you get two contributions. One contribution with a gap which was less than 5 millielectron volts, and one with a gap of about 12 millielectron volts. The higher energy one is actually the dimer state. So the dimer is in there, and it's emitting a bit, but not very much. It's dominated by the TADF. Right? Well, that's just a nicety in the system. Okay, so the question now is, we've got an Exiplex system which is potentially the best ever TADF material we've ever seen. How? What's it doing? So what we've done very recently is to try and see if we can understand what at least a potential mechanism for TADF in these Exiplexes is. So we took 3 systems, MT data, we had TPB, OXD7, TPBI, to make 3 different Exiplexes. Okay? You look at the spectrum, they all make really nice CT states, well redshifted. You'd think they should all be roughly the same. Yeah? So, let's have a look and see what happens to the photophysics. So this is TPD, TPBI. Right. So we look carefully at this system, and the numbers at the top are the calculated energy gaps between the CT state and the 2 local triplets, the local triplet of the TPB and the local triplet of the TPBI. So in this case, both triplets are a long way below the CT state. And you can see that you get virtually no TADF. You get lots of phosphorescence. Right? And in fact, if you look carefully at the power dependence of the DF, it's actually TTA. There's a little bit of TTA in there and nothing else. So that CT state, both triplets, a long way away. TPD OXD7, you see that one of the triplets is starting to get a bit closer, but the other one's a long way away. We get a hint of TADF. Okay. You get a hint of TADF there. You can see that the spectrum is the CT state longer. And if you look at the power dependence, it's kind of a combination between TADF and TTA. Okay? And you can see there's strong phosphorescence. So again, we're starting, as we get one triplet state close, we're starting to get a bit of TADF, but not a lot. So we pick our favourite MT data, put it with TPBI. And now, both triplet states are very close to the CT state. Though neither of them are quenching, both of them could couple. And surprise, surprise, what do we get? We get really nice TADF. Fairly strong temperature dependence. We get a lot of this power law at the end. So we don't really know. You look at the intensity dependence, and it's linear. There's no knee in there. And the emission doesn't really change. You don't see any phosphorescence at the end. Or very weak phosphorescence at the end. Sorry, it's down there. All right. So when we get to the point where we have the local triplet of the donor and the local triplet of the acceptor in resonance with the CT state, bingo, we get almost pure TADF. So we believe that we've got the same mechanism giving rise to the reverse intersystem crossing in these Exiplexes as you do in the ICT molecules. So you need that local state to mix to be able to get the spin-orbit coupling in the system. If you've got one close, it'll work, but if you've got the other one lower, you might get some triplet and some TADF, so you'd get TTA and TADF mixed. Okay? You don't want the CT to be well below the local triplets, because then you don't get any coupling and you won't get any TADF either. So as we understand it at the moment with the exciplexes, right, you've got the same, potentially the same mechanism to give rise to reverse intersystem crossing. But the donor acceptor aren't chemically bound anymore. The problem you've got is you don't know where the donor is with respect to the acceptor anymore. So you've got every possible conformation and distances. And if you think about it, it gives you a headache, and you think, well, how does it work in the first place? And you come back to what Crystal said. Do you need something which starts to pull these donor acceptors closer together to make them work? So is that why MT data seems to be exceptionally good at forming exciplexes which gives you TADF? Is it because it's got some kind of interaction that gets hold of the acceptor and gets it in the right position? I think the power law decay at longer times is showing you've got this big dispersion in energy gaps, positions, and so it's not a clean system. We have to work very hard to get the exiplex to be clean. But the devices can be made really well, and they're very simple. Co-evaporate 1-to-1, and you can get high efficiency. So I think there's a huge scope to understand what's going on in exciplexes. We really don't understand very much about them at all. All right? So I like leaving people with things to think about, so that's me done. Thank you very much.